All right, let's go ahead and get started. Today we're going to finish up on hash tables, namely talk about what's it called? Open chaining, open addressing, which is another way to deal with collisions. So before we get into that, I'll review what collisions are, talk about the problem, and then we'll talk about how we can implement open addressing, because there are multiple ways in order to implement it, and there's something additional that we'll need to know about called a load factor, and we'll get into why that's necessary later on. So first off, what's the problem? What causes a collision? Right, keys map to the same thing. So if we were doing our hash function with key mod 5, you insert 2, let's just pretend the length is 5. All right, 2 goes to 2, we're good. 21 goes to 1, because 21 mod 5 is 1, still good. 34 goes to 4, because 34 mod 5 is 4, we're still good. But then if we try to insert 54, we have an issue, because 54 mod 5 is 4, and we already have a 34 there. Yeah, review. I said we're going to do a quick review to make sure everyone's on the same page. All right, everyone got this? Yeah. How did we fix this last time? A linked list. We just made every entry a linked list. Let's see, we got a good picture. Here we go. And this is where the slides looked great. I think this one actually needs to go right up here. I think that's the problem. Yeah. So we talked about chaining, where we put everything in a linked list, and that was actually not a bad solution. So now we're going to do something called open addressing. So let's see what we have going on here. So in this one, we're still doing, looks like mod 8, so 15 mod 8 is 7, so it goes up there. Look at the bottom 2, object 5 key is 1, 1 mod 8 is still 1, that's great, 2 mod 8 is still 2, so that's good. Let's look at the middle 2, object 3 and object 2. The key is 4, so 4 mod 8 is still 4, that's good. But the next one you have 28, and what's 28 mod 8? It's 4 as well. But they didn't, where did they put it though? At 3. What do you think the pattern was?
First empty space.
The next empty space, right. So this one is a type of open addressing. The idea of open addressing is that you're not going to have any linked lists, you're just going to have the same array, and we're just going to try and find a different location to put your object. Yes?
How does it figure out, though, when you try looking with the key again? Because it's linked directly to index 4 according to search, so you go check 4 and it's not there. Does that mean you just check all the surrounding ones?
Yes.
Wouldn't that slow it down?
That's a great question.
Would the next open space? I guess the next open space could be after or before.
So would that slow it down? All right, hold on, stop. Think about the answer.
It's
Now,
binary.
good. All right, good. There we go.
Because it could get
Whew.
inserted all the way up, but say this for size 100. It tries to insert it at 0, but the next open one's 100.
So it has to go through the whole array just to get to it, right?
Yeah.
Well,
But
if
you
the
can-
array says 100, then there's no way we can put 100.
Yeah.
So what can we do to alleviate that problem?
Which could still, it would still be a binary search, right?
No, there's no binary search here, because you're not. There's no ordering to these. Because you put it right here, it may may not be there, may not be there, may not be there, may not be there. Okay, it's finally up there. You have to go through most of the array just to find it. What can we do to alleviate that problem?
Make sure it follows a specific pattern, which would speed it up.
Specific pattern.
If you can jump around.
Oh, if you can jump around. So instead of checking the next one, trying to randomize what the next location would be.
Or you could have a pointer.
Okay, yeah. So we could, or a point. Well, that's back to chaining. So that'd be a hybrid of the previous one, which is interesting, where you you point to the next one, but now you're kind of doing a linked list inside of an array. So not quite what we were trying to avoid, the linked list here. All right, well, let's go on. There's actually a couple of things we can do.
You could have something saved to like the previous thing that's entered.
Say that again?
You could have something saved that points to the previous thing that was entered, or where the previous information was entered.
Okay, I think you're thinking of a pointer to somewhere else, kind of like a linked list. So, but we're trying to avoid the linked list here in this version. All right, let's see what the slide says. So far, we studied hashing with chaining. There's others to store them all together with open addressing, where we systematically examine other indexes until an empty slot is located. All right, there's different ways to go about it. Oh, someone have an email? You don't want to share? It's not funny, or is it just?
No. It's
It's hilarious.
no. It's no.
Is it about hash tables?
I got a text. Definitely not.
Okay, I'll take that as a no. So if there's a collision, find an available array cell. So there's different ways to do it. You can do it linearly, where you just check the next one until you find it. You do a quadratic, where you take the location, you square it, and then mod it by the size of the array. Look there. If it's not there, square it again. Try and find the next one. That kind of jumps around the array, so it will hopefully alleviate this clumping effect. Or you can do what's called double hashing, where you hash it to one, it's not there, run a different hash algorithm to find the next one. You can kind of bounce back and forth between the hashing algorithms until you find another location. So let's talk about linear probing a little more, just so it makes sense to everyone that's going here. So you find a collision. There's a collision in the array. So you try and find the next index hash value plus 1, or then try the next one plus 2, and be sure to wrap around to the end array. If full, you need to throw an exception, or actually you need to resize the array. Don't throw an exception. Exceptions are terrible in C++. Well, Java, they're part of the language, but in C++, when you throw an exception, it really slows down your program a lot. And I don't, wow, there's no eraser? There they are. All right. So, linear probing. Guess it's just going to be Christmas today. Yay! Okay. I would ask, give me some numbers. Well, actually, let's do it that way. I always like that. Give me some numbers.
It's kind of like a
There's 373.
very light colored pen.
Yeah, that's hard to see on
If it's useless, it's useless.
Gotta get out the special markers.
All right.
Hey.
Oh, how's that?
That's
Wow.
a nice marker.
It's too dark.
Well played, sir. Wow, that is really dark. 0, 1, 2, 3, 4, 5, 6. What's that? Another one. 7. There we go. So we're
37.
Hold on. 1, 2, 3, 4, 5, 6, 7. I'm going to erase this last one. Sorry, guys. A little tired today. There we go. Now it's going to make more sense. All right. So 7. Where would 7 go? First one.
Left.
Great. Where would the 3 go?
The next one. To the second element of
Yeah, second element of the array. Oh, wait a minute. No, it wouldn't. It would go 0, 1, 2, 3. So it would go up here. Nice and squeaky. So you did 73. I hope that gives us something good. Oh, it does.
I think it's
It goes to 3.
It goes to 3 again. So we got 73 as intended. What if we then did 72?
Then we had to do 1, I guess.
Yeah, it would go over here. Then, just to be that way, let's add, what do we want to add next? 70. Where did that guy go?
Do 6.
Yeah, he can't go here, so he's going to go back up to the 6.
Why?
Well, 70 mod 7 is 0, but 7's already there. So we need to go down by 1, but you can't do -1, right? So we go up to the top, and now he's at 6. So we'll go ahead and add 74. I think this is going to be the big one. So not 74. That was not the number I wanted.
Sure.
No, it was totally not what I said. How about 143? Yeah, that's much better.
Okay, so 5.
So, what's 143 mod 7? 3. So it would go here. We can't go there, so we go to the next one. Can we go there? Go to the next one. Can we go there? Go to the next one. Can we go there? Oh, we gotta go to the top. Can we go there? Can we go? 17. All right. Yeah,
No
140.
matter what number's next, it's gonna go in.
All right. Well, let's stop there. Yeah, it has to go in 4. But here's where another problem is. What if we want to do? We're gonna search for 173 or 143. Keep wanting to say 7. What happens?
So once again, we start at 3 and then all the way to 0. That's
We have to
0.
keep going until we either find the number or find an empty spot. But hopefully you can see from here, we just went through most of the array, which just made it an O of n, essentially O of n operation. So what are some things we could have done to alleviate this problem?
Start from the empty spots on the back. Or not up new array.
Well, if we're right here, how do we know the empty spot's right here? We have to go and search. We want to avoid searching, scanning arrays. So we have, 7 elements, and one of them is, we could try double hashing or quadratic. One thing I want to point out with this, we have a hash table. Is it mostly empty, mostly full, or about 50-50? Mostly full. If you're doing open addressing, do you want your hash table to be mostly full? No. This is why. So, when in general you have something called a load factor, I'm sure the slides will talk about this soon. Nice and squeaky. We'll call it 0.75. The idea is that once your hash table is 75% or more loaded, you need to increase the capacity and then rehash everything. Okay? Well, hold on. Think about this. Just for the sake of argument, we'll increase it by, we'll double it. But watch what happens when we double it.
Oh yeah, you have to go through the entire array again.
8, 9, 10, 11, 12, 13. Oh, that's a beautiful box. 14. Okay, so you got to rehash all these numbers.
Then you just make a better hash function.
Well, there's still going to be this clumping effect when you have a small amount, and that's the problem. You want to avoid that. All right, so we doubled it. Where is 7 going to go?
No, sir.
No, it's going to go 7 now because we have that available. Where's 72 going to go? Oh man, I made this hard for me. Why did I do this?
9 or something.
What's that?
We'll go to 9.
We'd go either go 9 or 1.
Either
Or
or.
either 9 or 2.
Whichever one's open.
But
So 28.
14,
What's 28?
42,
40. Yeah.
56. Wait, there's 70. Okay, so we'll go to 2.
It would go to 2. Okay, great. 2. Where's 73 going to go?
Just
There
3.
we go. Where's 3 going to go?
2, 1.
Uh-oh, it's going to go to 1. Oh well, that's fine. Where's 143 going to go? Wow, I made this hard on me. It's going to go down to 0. And then 70. 13? Okay. So still a bit of a clumping effect, but searching for 143, you don't have to scan as much, but searching for other numbers, you're going to jump to it. This is usually the way people fix clumping in your hash table.
Is that any better?
Notice you don't have to scan the whole array to find certain numbers.
What
you have to do a lot more scanning up here than down here. So your remember with hash tables, you're mainly concerned about search. Insert, you want it to be 0, 1 in insert, unless you have to resize it. But you're really concerned about searching because that's what hash tables are usually used for. You throw a bunch of numbers at it, and you just want to find things really fast.
But what if you needed to find 7?
No, you just go right there. Because search for 7, boom, it's there. It's 0, 1. You don't have to scan. You just hash straight to it. Yeah, 3, you gotta scan a little, but not a lot. So it's better. It's better. Okay. Y'all see what's going on?
No.
No. All right. What part is missing?
Why does 7 mod 7 have a remainder of 7? Why do you guys 7?
7 mod 14 is 7. The length of this is 14.
Oh,
So you're
we're
modding
on
it by the
14.
length. Yeah, over here is 14, so you're modding it by 14. Over here the length is 7, so you mod it by 7.
So we mod the, then it's like 7.
Okay.
That helped?
So then we're gonna-
A little bit. Now your question was about 3. 3 would go here, but we still have to scan until we find it. But we don't have to scan as long as opposed to with 143 where we had to go through most of the array. This one you just go through a part of the array.
Why is it if you search for 7, you would go straight to 7?
If you search for 7 over here, you would go straight to 7 because 7 mod 14 is 7 and there it is.
Okay.
Remember, you start with the hashed function of your key.
Yeah. Yeah, you always hash the value first to get the location that you want to start your search.
Gotcha. That makes so much sense.
All right, so quadratic probing, variation that causes more complex to be calculated the next try. They're not even going to tell you. Okay, great. So over here, whoops. You can do different types of quadratic probing, but for example, let's see, where were we? I just don't want to write these out again. So 73 would still go down here. 72 would still go what, right here?
If what?
We're doing quadratic probing. So you're still going to add things. The problem is when you have a collision, like if you were to add 3 right here, it goes to 73. I mean, it still goes to this slot, but since it's there, instead of trying to search down, you could do different things. Like you could take the index and cube it, or square it, I'm sorry, which would put the 3 up here. That way you only have to jump once. And the idea of this is, I'm just using squaring as an example. You can use any type of formula that you're, how complex.
So what if you,
What's that? Why did I square it? I ran a bunch of statistics and found out squaring was useful.
so if you square it, it goes over the size of your array. Does it jump back to the beginning?
So we add 73, we add 72. This is our other, I'm sorry. Maybe this will make more sense. So this is linear, and we're using quadratic over here. Okay?
So 2 different, like, so now we're just pretending like we're just.
It's the same length, but we're using a different type of collision resolution algorithm.
If you
Okay.
have one less cell in the right one.
Yeah, where am I missing it?
The bottom.
Oh yeah, look at that. There we go. So 73, I think we said would still go there, 72. 3 would still resolve the 3, but we're not going to go to the next value like we would with linear probing. I'm just saying we're going to square what the index was and go there. So it goes up to 9 and then puts the 3 in there. All right, great. 143, that would also resolve the 3, so go to 9. It's already there. What's 9 squared? 81, which is what? 11 mod 14? All right, sure. You see how it's avoiding this clumping effect by jumping around? And then 70 would still go up. So You'd still have some type of chaining, but you would, I mean,
Would
so.
70 go to 0?
Which one? Oh, yeah, you're right. There, now we don't even have to do any chaining with that one. So it avoided some chaining with that number because it's not clumping together. So what's nice about quadratic is it avoids the clumping. The idea is your resolution algorithm, you just want to kind of jump around as much as possible. We're sticking with linear for this class mainly because it's easy to implement. But do keep in mind that for advanced implementations, like what the STL would use, they're going to do something that gives you a better distribution.
All hail the mighty STL.
What?
All hail the mighty STL.
Right. Don't reinvent the wheel. Learn it and then use it, and then use what they do. You know. So that's quadratic. You could do double hashing. You basically apply a second hash function after the first. You know, array index plus the step size, pound the, mod the array. You can do a bunch of different things. I did quadratic here. We could pick whatever hash function we want. But when you do the second hash, you usually want to involve the array index that you're at plus whatever it is, step size, something, just to jump. And you want, prime less than the array size is usually a good selection. But I'm not going to ask you to code that. I'm only going to ask you to code linear probing.
How is quadratic like much harder than linear?
So the problem is, what if you want to delete?
Don't.
So you still
Oh,
the
you
best
gotta
answer I have,
check to
don't.
see.
Right, ignore the problem, okay? That's always an answer.
You gotta go through, check all the possibilities.
well.
So like if you delete the one at 3.
So let's start with the linear, right? We want to delete 143, right?
It's not gonna be just.
So we, not there, not there, not there. Oh, it's 143. But we also need to check this guy to see if he needs to be moved, right?
Yeah.
Right, and hopefully you can see if there's a long chain here, you might be fixing a lot of things and moving them around. And with quadratic probing, if we want to fix 143, well, this one's not too bad because you go to 143, then you have to quadratic again, find the next one, and then jumble it around. It's only, when I say it's hard to think about and figure out. The algorithm's still the same.
So basically, like, we want to fix things when we delete.
Yeah, you have to fix it when you delete it. Yeah, delete's going to be the hard function here. All right, load factor. Okay. So understanding the expected load factor, it's going to help you determine the efficiency of your hash table. In general, for open addressing, if it's less than 50% full, you're wasting a lot of space. And if you have greater than 80%, you have what they call it overflows significant. Basically, you're going to have a lot of collisions when you try and search, which will make your hash table very inefficient. So that, and how they find these numbers? Take a guess. Statistical analysis. There you go. All right, perfect. They found out between 50 and 80%, somewhere in there is good. I don't remember. I think Java does 0.75, so 75%. It depends on your implementation. But that's open addressing. For chaining, which usually has a load factor, we didn't implement one because it's not needed per se. If it's less than 1, you're wasting space. Greater than 2, search time may be significant. What is this? Wait, think about this for a moment. Because if you're open addressing and your load factor is 1.0, what does that mean?
Yeah, it's full. It's full.
It's full, right? So you can't add anything more because it's full. But if you're doing chaining and your load factor is 1, what does that mean?
That every item has like 1 element.
Not necessarily.
The array has one list per cell.
Not necessarily, because you could have the top half have 2 and the bottom half have
so
none.
it's
The
average.
same amount of
Yeah,
elements
this is the
have
average.
been added as the array size.
Right, as the array size. But can you still add more items in chaining?
Yeah.
So in chaining, you can have a load factor greater than 1. Open addressing, if it goes above 1, you have a coding problem. You're putting stuff where it shouldn't be. So
Yeah.
You've done something.
something bad just happened.
Sad.
Sadness has occurred, exactly. So with chaining, having something greater than 1 is actually somewhat advantageous because it helps you estimate, estimate its efficiency. Because remember, with a linked list, if you have to search down 2 or 3 elements, that's no big deal. So they've decided that if it's less than 1, you're kind of wasting space because a lot of your entries have no items in it. Greater than 2, it may start taking a long time to find something because you might have a certain entry with 7, 10, or many items in it. And yes.
So which would you prefer, open addressing or chaining?
I was going to ask you that question. Nice looking ahead. Before we get to that, again, how'd they figure out these two numbers, 1.0 and 2.0? Good. Now, which of these two is better?
Depends.
Man, y'all are doing great.
We're gonna change the world.
If you have a really good hashing function, the chaining would be better, right? Because then you can make it that you have less open spaces.
Okay.
So what does it depend on?
Exactly. What would it depend upon?
The size of it?
So some of this is getting into computer architecture, which you'll learn about, actually not next semester, but the semester after. Well, let's think about it this way. What if you had a very fixed amount of memory?
For the chaining. No. Then you get a second dash.
Yes. What's that?
That would be open address.
Yeah, open addressing, because you'd have to specify your exact hash table size. So that's when the open addressing would be good, because you just reserve the memory you're allowed, and then work with what you got.
So then like the user tries to add, but you have no more memory, just like fail to add.
Yeah, fail to add. But with chaining, of course, if you have plenty of memory, and we're going to say, if memory was really fast, which unfortunately it's not, it's incredibly slow, but if it was really fast, then chaining would actually be a little better, because you could probably, you could jump around, it's easier to move around, and your memory operations wouldn't be slow. The thing about open addressing, why it's used, is it ends up being, just because of computer architecture, that you can keep your hash table or a good portion of your hash table memory that is advantageous for performance reasons. So it ends up being usually open addressing is used over chain. Which of these two would you prefer to implement if you had to do it?
Chaining.
Chaining, yeah. Chaining is just straightforward to me. Open addressing is like you're using a trick. It ends up being that open addressing, when implemented correctly, will be faster. But you can think of it as chaining because both of them are going to implement the same interface. But keep in mind that most of the time, behind the scenes, they do open addressing instead.
Well, I'm guessing if you implement the chaining with quadratic, it's going to be better. It's going to be.
Well, no chaining. There's no conflict resolution,
sorry,
right?
not
You just add it to the linked list, yeah.
I'm not chaining open.
Oh, open addressing, yeah. Yeah, what they do is they do open addressing. They don't do linear probing. They do their own special formula for it.
It's just a more complex version of quadratic, which
Yeah.
has been proven to be fixed.
Correct. They ran a lot of statistics. Someone came up with a formula. There you go.
Some math nerd.
Some math nerd. Wow. All right, deletion. So we talked about deleting. This is where sadness occurs when you're doing open addressing. So we have, let's look at the left. We have an array size of 7. We've added 0, 1, 2, and then when you added 7, it had to go to the very end. And then you have 0, 1, uh-oh, you deleted it. Now you got to go back to 7. Well, you must use lazy deletion on search and treat a lazy delete item as an empty slot. Okay. Oh, there's different ways to go about this.
Oh,
There are.
there's a graph.
And we're not going to talk about that real quick. Wish the slides explain this. So, there's the easy way to code this and the hard way to code this. Hopefully y'all will choose the easy way.
Well, hopefully you know.
Yeah, I know. So let's say where's 143 is right here. We want to delete 143, right? And we're doing linear probing. We would delete here, Now, do we need to do anything to the 70?
Yeah.
So we either could try and keep going and move the 70 down here, or you could mark it. Now, let me tell you what this means. You can try and either fix the array, which is hard, or you could just say, we just deleted this and we're going to mark it as deleted. So when you go search for the 70, you check to see if it's here. It's not there, but it's marked, so you need to go and keep searching.
Okay, so could you do like a vector of indexes which are marked so that if it's empty and the index is not in the vector, you keep going?
Right, you can do it that way. Or you could have your hash table be of a pair, remember STD pair, where you'd have the item and then Boolean is marked. That'll work as well. Yes?
Okay.
Yeah.
When you get to the whole thing, if you have marked every one, your searches will become.
Oh, then.
And I assume there's resetting as soon as the whole thing is empty, even though you deleted it?
You could do that, yes. Open addressing's a pain. That's why you have someone else do it. All right, some graphs. Let's see what we got here. Successful searches. So notice that we have linear probing, double hashing, and separate chaining. So chaining's at the bottom. Right there's a load factor. Hopefully no one is surprised that with a load factor at 1, chaining's going to win, probably because you're not that loaded up, as opposed to the other two where it just gets bad really fast.
Yeah.
Notice at 0.8 things get sad.
For everything but chaining.
Right, well, chaining, for this to be fair, you'd have to be over here in addressing chaining. So this graph is not, I guess, giving a equitable or equal representation of chaining, but it is supposed to show you that double hashing is significantly better than linear probing.
Where would the quadratic probing be?
So it'd probably be somewhere in between.
Between what?
Linear probing and double hashing. And then what's this one? Oh, the load factor for an unsuccessful search. So remember, they found it successful, they didn't find it. Yeah, it's even worse.
For linear, you have to literally go through all the way.
Exactly, yeah. Again, separate chaining apparently looks like the best, but that's simply because it's using a linked list, and really it'd be over there is where it'd start. Well, it wouldn't even go up due to chaining. Okay. Open addressing versus separate chaining. When should you be concerned about which one? Well, I guess it depends. Let's see if the slides have something else to consider. Do you know the total number of items to be inserted in the table? If you do actually know that number, then open addressing might be pretty good. But if you don't, you probably wouldn't go with chaining. Do you have plenty of memory? If you have very fixed size, then, well, you may want to go with open addressing so you can just reserve how much you can have and then call it in. Do you know what your load factor is going to be? This has to do with, are you going to be doing a lot of searchings and deletings, or are you just going to add a bunch of stuff and then try and search for it later? But if you're going to add some stuff, do a lot of searches, remove, add, do a search, remove, add, that's going to change up pretty much which one would be best. Probably would be chaining in that case. Because as you can see, trying to delete, if you delete a lot with open addressing, sadness
You're gonna
occurs.
have a bad time.
Yeah, you're going to have a bad time, yes.
So in Java, I think we briefly discussed what the difference between hash table and hash map was, but I think it was like
It's been a while since I've looked it up. Last I checked, if I recall correctly, hash table is not thread safe, but hash map is. You know what I'm talking about?
That sounds right.
We've talked slightly about thread safe.
So thread, we're not doing thread. We're not doing multi-core programming. And the way you do that is you have multiple threads, which means you have multiple lines of execution happening at the same time, simultaneously. And the problem is that both of them simultaneously try and do an insert on a hash table. If it's not thread safe, sadness is going to happen. If it is thread safe, then one of them will be committed before the other.
So what's the advantage of hash table?
probably speed, but the real answer to your question, hash table is old, hash map is new.
Okay.
Alright. Alright.
Oh yeah, besides that, they're the same thing, basically. Oh good, more about hash tables in Java. You can set the initial load factor. The default's 0.75, got that right. Java, oh yeah, here we go. Hash tables were so important to Java that all objects have to have a hash code function which return a hash code for their object. That is how important this data structure is. And it's not just they added this at some point. This came with version 1.0 of Java. They required everyone to be able to go to a hash code for their function. That's how much the writers of Java value hash codes. And when you go out, these are hash tables, sorry, and hash tables are used a lot. Some people will say, when in doubt, just use a hash table. Oh, have we? I don't think we've exactly answered why that's the case. So let's go and make a beautiful graph, beautiful chart.
Discuss why what?
What's that?
What are we discussing here?
You know, it's the great data structure shootout, right? What's the best data structure? It depends. That's an algorithm.
But still,
So like make the best data structure.
Yeah, what's the best one? We'll do
Data structure that whole double sort.
we'll do random insert. All right, random insert. If you were to randomly insert into an array, what's the big O? O of, someone said it. And why is it O of n? You got to move everything over. Yep. All right, linked list. Well, that's a tricky one. It's kind of this is hard to apply to a linked list.
yeah, what's the random?
Yeah, randomly. You have to find the correct location. So we'll say, how about instead of random insert, random/ordered? You have to find the location and insert it, so you're still scanning the whole linked list. How about a binary search tree? Which one? Log n, or O of n in worst case. Because if it's not balanced, it's a linked list. All right. Yeah. So now we go to hash table. Well, you're just inserting, you can't do it by order. So how long does insert take in a hash table? There's no log. O of 1 on the average case, O of 1. O of n in the worst case. All right. How about search? And we'll go and say these are ordered. Oh, that was nice and squeaky. If the array is ordered, how long does it take to find something? Log of n, because you can do a binary search. Great. The linked list is ordered, how long does it take to find something? O of n. The sorting doesn't help us. Binary search tree? Hey, look, it's the same thing as above. Yep. How about a hash table? There's no order. Well, it's same as above. Yep. Yeah, there's going to be a pattern here with the hash table. Hopefully you'll be able to see it. Hey, let's do delete. Yeah, you got to move everything over. Sadness. How about a linked list?
Also, then
Yeah,
because
you got to find it. Binary search tree. Same with everything above, right? Hopefully it's just log of n, unless you have to go. It deteriorates to a linked list, and then hash table. Yep. All right. So what's the best data structure? It depends. But this is why hash tables are usually a default data structure, because in the average case you have O of 1 for most things. And a lot of the time you're just, if you have O of n every once in a while, you're okay with it. Unless, of course, you're a piece of health equipment and it's keeping someone's heart alive or something. But most of the time, that's not the case, so O of 1, average, we're good. Okay. Oh, that was it. Wow, I just went through all that. 45 minutes. All right, I guess we'll go and start doing some coding with your lab. Any questions about open addressing? There will be. All right.